All right, so let me get you started on some of these problems. Now, like I said, this is not due until Tuesday. I'm going to tell you right now, don't even try problem number 7. 7 won't make any sense until tomorrow when I do this demonstration of space-time with Einstein's view of gravity. Okay, so for now, don't even worry about number 7. It's going to take you a lot of space, so if you do want to work this and you want to space this out, leave a lot of space for question number 7. That's the biggest, most complex problem on the assignment. Don't worry about the questions out of the book. Don't worry about those for now. Some of those we're going to work in class like tomorrow, so don't even worry about those. So your best case scenario, if you wanted to get a head start, is if you could work 1 through 14, okay? But do not worry about question number 7, because you just don't know enough to do number 7. We'll talk about number 7 in class tomorrow. Now, one of the things you're going to need, and this is up there at the top, I've given you the constants. There's an appendix in the back of your book. It's page A7. And it's this section that has it's got like a blue line around it. So you need what's on page A7. So up here, and this is going to be the problems out of the book, okay? So up here you have like astronomical data. So when you get to some of the questions out of the book, which don't worry about tonight, but I'm just pointing this out, you're going to need to reference this chart, okay? So don't worry about it for now, but you're going to have to deal with that later. So let me get you started on some of these problems. So on number 1, visualize this. You have 2 identical spheres that are a known distance apart of 1.20 meters. Okay? So 1.2 meters would be about like this. So you've got these spheres that are known distance apart. You measure the gravitational attraction between them, you know, like Cavendish, like you measure the torsion wire. And you've got 1.00 times 10 to the negative 4th newtons. Okay? You want to find the mass of each sphere. So what equation are you going to start with? Andrew. What's the most basic equation to calculate gravitational attraction between 2 objects?
The GM.
Yeah, big G, M1, M2 over D squared. You know the distance between the 2 objects? Yep. You know the force between them? Yep. You know what big G is? Yep. But the mass has created a problem. So if you let mass 1 have a value of x, what's going to be the value of mass 2?
X.
Why?
Because they're the same. Identical.
They're identical. So you're going to have x times x, which is going to get you
2x.
solve for x. Now, when you get to question number 2, it says, at what center to center distance from the Earth would a 1 kilogram mass weigh 3 newtons? So there's a couple of ways you can work number 2. One option is that you go to that. F equals big G, M1, M2 over D squared. You know what you want the gravitational force to equal. You want that to equal 3 newtons. You know what that number needs to be. You know what big G is. It's the Earth and this object, which has a mass of 1 kilogram. So that would be the mass of the Earth. That would be 1 kilogram. Solve for D. So you've got the force equal 3 newton, and that's what it's creating, is a 3 newton force. Big G, the Earth is one object, the 1 kilogram mass is the other. Solve for D. That's an option. It's an option. Option number 2 is that if you look at FG equaling MG, right now, right now in this room, what does a 1 kilogram mass weigh? 9.8 newtons. Why? Gravitational acceleration is 9.8 meters per second squared. Now, we just showed if Luke is standing on top of a ladder, 174 kilometers tall, this thing weighs less than 9.8. It's like 9.3, right? So, if you want something to weigh 3 newtons, what does the gravitational acceleration have to be? Do not make this difficult. 3 meters per second squared, right? So the other option is that you go little g equals big G, mass of the earth over r squared. What do you want little g to equal? 3 meters per second squared. You know what the mass of the earth is, you got that number, you know what big G is, solve for r. Either way. When you get to question number 5, notice that this is about the Lunar Command Module orbiting the moon. Lunar Command Module orbited 72 kilometers above the moon. I gave you the radius of the moon. What are you going to do with those two numbers? Add them or subtract them? Add them, because it's 72 kilometers above. So, when you get to question number 9, question number 9, 8 and 9 is what are you going to use that Swiss Army knife equation? Okay? I've given you information about Mimas, moon of Saturn. I've given you the orbital radius of a period of 23 hours. What is the mass of Saturn? So you need that one equation, the Swiss Army knife, solve for the mass of Saturn. Okay, so here's the plan for tomorrow. We're going to go through, we're going to work some of these problems. I'm going to give you a visual idea of what Einstein viewed gravity as. It was a warping of space and time. We're going to do some more explanations on these equations. We'll review on Monday, test on Tuesday. So do not wait until Monday night to try and get this assignment done. And if you have any questions, like tomorrow I'll say, hey, anybody have any questions? For those of you that attempted it, like I said, do not even think about trying number 7. We're going to talk about number 7 in class tomorrow. Yes?
I would like my assignment, please, because I don't know.
Okay, Andrew, stop you on the camera.
They already got